Hey, welcome back. Today we're going to be talking about how to solve for the angular acceleration of a pulley using net torque and net forces. So this lesson is designed primarily for AP Physics students, AP Physics C Mechanics and AP 1, but this could also be done with a solid physics class, like maybe an honors physics class or something like that in high school. There's no calculus here, and it does summarize a lot of concepts that we've been talking about lately. It's an excellent problem to think through and to prepare for an AP test or just to understand the material better and how to approach this. And I want to start out by contrasting our strategy here with problems we may have done in the past with a Atwood's machine is the type of pulley problems that we're talking about. This pulley system has a mass. You cannot ignore the mass of the pulley. And as a result, because the pulley is not massless, you have to think about the torque and the mass of the pulley itself as an object. So we cannot assume that tension is the same, like the tension on mass 1 is equal to the tension on mass 2, like we would for a massless pulley system. Here, we have to treat it differently. I've got a little explanation here. If you want to take a moment to read, go for it. Otherwise, we're going to get to the problem. Let's go ahead and get to it. Oh, one quick but actually very important thing that we need to talk about is going to be this. Remember, we need to figure out what the direction of the vector is for the torque because that causes the acceleration. So this was our equation. It's a cross product. I'm going to show you how you would apply that in this case. Remember, our first vector here is going to be the r vector. In other words, the order, this is the first, and this is the second. Literally, the order matters when we apply these things. So the first vector is in that direction. The second vector, we could say, is in this direction. So the force is applied like this. Now, I've done a whole video on this, but I'm going to talk you through it briefly. Use your right hand and have the palm of your hands point in the direction of the first vector. That would be to the right. And then curl your fingers in the direction of the second vector. And so you're curling your fingers up in front of your face. What is the direction of your thumb of your right hand pointing right now? Well, that would be right out towards you. And so we could call that like a positive Z axis. If we wanted to set up an axis here, we could say like this is X and this is Y. And then this is hard to visualize on a two-dimensional screen, but if you think about this axis, if we wanted to call this the positive Z, sometimes you could call that a negative Z, like you could reverse this as well. But that's one way of addressing this, is that it's coming out towards you, the vector. Alright, let's go ahead and get to the math. Although I do want to say this part right here is actually really important. We can't just ignore it, we do need to think about it. But let's go ahead and get to the math. Okay, and so let's start thinking through our strategies that we've been talking about for this class and how to approach this. So if we start focusing on M1, first of all, we can think about our free body diagram. Maybe I'll save some space and draw it over here. We've got force due to gravity for 1, and we've got a tension. We're going to call this tension 1. Tension 1 is not necessarily tension 2 because the whole disk has mass and it's rotating. So if we think about the sum of our forces, or you could say the net force in the y-axis on 1, we've got, let's go back over here. Let's call down positive and up negative here. And I do want to use this convention because this is typically what is done. You're going to have a torque that we will call counterclockwise. That will be positive in general. And if you have a torque or a net torque that is clockwise, we're going to call that negative. So what you want to do is think about if there's a force, like our force due to gravity here, for M1, that's going to cause a counterclockwise torque, then we'll call that positive, and up we'll call it negative. And if you start to think of this as a system, it can be helpful because it will help us to avoid issues with positive, negative things that'll pop up otherwise if we don't do this. So this is helpful if we say down is positive here. When we draw the free body diagram for M2, I'm going to say M2 is going to be less. This is force due to gravity for 2, and we're going to have tension. Tension should be greater here. So we could say tension 2 is greater. And if we take a look at that, we can say, well, let's call, in this case, let's call up positive and down negative. So you could argue, hey, that's inconsistent. And the answer is sort of. Depends how you look at it. If you look at it as what's going to be a positive or a negative torque, it is actually a consistent one. All right, so there's some of our forces. We're looking at M1. We could say, what do we have? Well, we've got FG1. And that's going to be a positive value. And we literally are summing up the forces. That's why I call it the sum of the forces strategy. You can also think of this as just a net force is one way to talk about that. So you have a negative T1. And then the second line for the sum of the forces strategy is to write is equal to MA. We're going to leave it as just acceleration for now because the acceleration for M1 is the same acceleration as M2, and in fact it's the same acceleration as the disk at the outermost edges in terms of a tangential acceleration, so to speak. So we can set these equal to each other and say Fg1 minus tension 1 is equal to M mass times acceleration. Oh, let's break this down a bit. This is going to be M1G minus tension 1 is equal to M1A. And that may be where we stop for now. We're not quite sure, I think, at this point of the problem, like, where are we going with this? What's a helpful strategy to address? So what we're going to do instead is just use our general strategies and think through the process of how you would actually solve for this. So you would say the sum of the forces in the y for 2, and if we take a look at 2, we've got tension 2, and we've got plus and negative Fg2. Say plus and negative because we're talking about summing up the forces in that axis. So sum of the forces in the y for 2 is equal to mass 2 times acceleration. That's Newton's second law. We can set these things equal to each other and say tension 2 minus Fg2 is equal to M2A. Alright, fair enough. Let's break this down a little bit further. Minus M2G is equal to M2A. So now at this point, I mean, one thing that comes to mind is if you take a look at that, we've got acceleration in both equations. We could set them equal to each other, but all that's going to do for us is set up a ratio or a relationship of T1 to T2. Not the most useful thing at this point, so let's, again, just hold off on that just for a moment. Okay, so we could look at the torques of each object individually, but there is one really big thing that we haven't even touched yet or thought really much about. What do you think that is? Okay, the main thing that we really haven't even thought about yet is what's going on with M3. Now with M3, the mass of the disk, what we're going to need to do is think about the sum of the torques. Think about the sum of the torques on the system as a whole, so to speak. So sum of the torques for 3. Let's think about this. And there's effectively going to be two torques here that we have involved. So we've got the torque from M1, based on the net force, you could say. We could, again, call that positive. And then this is going to be the torque from M2. And we could say, well, let's think about the sum of the torques on 3. Or you could think of this as like the whole system. And that's going to be equal to I times alpha. And we can set these equal to each other and think about what's happening here. So you could say torque from 1 minus torque from 2 is equal to I times alpha. Just to be clear, that I stands for the moment of inertia, or it's also called rotational inertia, and it's the rotational version of inertia. Now, let's isolate for tension 1, and that can go into this equation that we're going to be working with here. And let's isolate for tension 2 over here, so we could say this is true. Alright, so now we can say, well, those two tensions are going to be embedded in this new equation we're going to be working with. So I'll sort of draw all three of these together and say this is going to be tension 1. And where's that tension 1 applied at? Well, that's going to be applied at the radius. And the second term for this equation right here, so I'm using this bottom equation and subbing in the top equation. So we could say this is true. Let's make this a minus. And so minus tension 2 times the radius, because that's where the torque is applied, right, is equal to I times alpha. Okay, so now at this point, it's really important to start asking ourselves a little bit more detail also about this cylinder. So the cylinder, it's a regular shape, and hopefully what I'm about to say you can start to anticipate. We need to plug something in or sub something in for this moment of inertia. And so what we're going to sub in is going to be 1/2 mr squared, because that's going to be our rotational inertia here. Now notice that we've got an r in every term. So if we have an r in every term, we can divide every term by r. So now we can say tension 1. Before I sub in a bunch of stuff and divide stuff out, let's just simplify at this stage. So I'm going to get rid of the r here, say tension 1 minus tension 2 is equal to 1/2 mr, one of the r's remains, and I'll put that in parentheses, times alpha. Okay, and at this point it's really useful to think about this. I've called it a small but mighty equation here, where we can relate a linear relationship with a rotational relationship. And then there is an analog here with acceleration. So we could say we've got our acceleration. Let's change this out and say, well, what if we said alpha is equal to a over r, and took that and subbed it in here. So then we would have tension 1 minus tension 2 times a over r. Notice these r's go away as well, and I am out of room. Okay, and I'm going to put check marks by the two tension equations that we solved for previously, just so we can track what I'm doing here. So here, let me write this out. Okay, and so notice we do have some terms with acceleration and some terms without it. Let's pull our terms with acceleration to the right. Okay, very good. And so now at this point, let's factor out our acceleration. Okay, and I'm running out of room, so I'm going to write this over here. And so that's going to be our acceleration. Now, the key part of this problem at the end that we need to remember is that we need to use this equation and go back into angular acceleration, because that's what the problem is asking of us. So we now have our acceleration. Let's think about what this would be. So we want alpha. So alpha is going to be equal to a over r. Well, we have a. All we need to do is take this right here and change this. So I will change this to an alpha now, and we need an r value down below. So we're going to add in that r value down below. This is how you would approach a problem here to be able to solve for the angular acceleration for a pulley system. And so yes, this is complex. Yes, it actually draws on a lot of concepts that we've talked about in this unit, but there's nothing in here that cannot be done by an AP Physics 1 student or just a good honors physics student. And so, yeah, hopefully this makes sense. I will say this, I've done screencasts on an entire year of physics, as well as most of the ideas for an AP Physics E mechanics class. So if you have any questions or comments down below, please let me know. And I hope you all have a great day. Take care.